what have we done over here? We've made sure that all the D flip-flops have the same clock. All the muxes have the same select lines, so all of them do the same function at any given point of time. The output of each respective mux is connected to the respective flip-flop, and the output of the flip-flop is what you're observing. The inputs of the muxes is what we haven't decided yet, and we haven't accounted for any of these functions yet. So how would you do it? Now, when it is a 0, 0, let me just go ahead and label these lines too. Let this be 0, 1, 2, 3. Now, if I want to hold on to the value, that means that if these select lines are 0, 0, this line is going to be selected and will appear at the output of the mux. The output of the mux is what is connected to the flip-flop, right? If I want to hold on to the value, all I have to do is connect the output of the D flip-flop to the line 0. So at every clock pulse, the output of the D flip-flop, which is Q, which also appears over here, will be selected if these two lines are 0, 0. If this is 0, 0, Q, which is the output currently, will appear at the input of D. And so, at the next clock pulse, the output is again going to be the same value. If this is 0, 0 appears over here, 0 appears over here. At the next clock pulse, again 0 is going to appear at the output. You see that? It's like a loop. But I'm completing the loop by connecting Q to the line 0. This will work only if these two lines are 0, 0. If these two lines are not 0, 0, this part is disconnected from this entire part. And so you will not see the same output over here. Do you see that? This is a connected graph. This is a closed loop. Only if these two lines are 0, 0. Only when these two are 0, 0, this Q appears over here. Otherwise, it's not going to appear. That's why when these two select lines are 0, 0, it is going to do the function of holding on to the value. And that's the only function it's going to do. Yes?
So the mux is not a mux of the input values, it's the mux of the functions?
Come again?
The multiplexers, they're of the functions or of the input values?
You have to perform these functions using a circuit. The output should appear as if it was constant. It did not change, even if the inputs change. Now, if you see over here, actually, give me 2 more minutes, and I think we will get to that point.
Okay.
It shouldn't be so difficult to understand then. First thing is clear is that even if the clock is changing, even if you see a rising edge on the clock, the output is not changing, the output is remaining constant. Is that part clear? So the clock has no influence on the output if S1 and S0 are 0, 0. And so it is holding on to the value. Let's look at 1, 1. 1, 1 implies that I should do a parallel load. For a parallel load, obviously you need to have external inputs, right? 1, 1 implies these two lines are 1, 1. If these two lines are 1, 1, line 3 is selected, right? Before we get to that, all of them should basically do the same thing. So when these two, coming back to parallel load, when it's 1, 1, 1, 1 implies line 3 selected, right? So at line 3, if I provide an external input, then this input appears over here if these two lines are 1, 1, right? And if I provide a rising edge on the clock now, this input which appears over here will appear at the output, at the rising edge of the clock. Do Do you see that? This can happen only if these two lines are 1, 1. And if I provide parallelly inputs of I2, I3, and I4, if these two lines are 1, 1, line 3 on each and every mux is selected because all of them have the same select lines. Right? And all of these inputs will appear at the inputs of the D flip-flop. The output of the mux, which is the input of the D flip-flop. It will appear over here. And given that the clock, if you provide a rising edge on the clock, this input, which is the input of the D flip-flop now, will appear at the output for each and every one of them. So provided this is 1, 1, I1, I2, I3, I4 appears at Q1, Q2, Q3, and Q4. And that is a parallel load. Okay? Next. At 0, 1, it should do a right shift. Right shift implies it should move to this side. Actually, you know what? I think I was wrong. Yeah, you have to look from your perspective. This is the left shift, this is the right shift. So, at 0, 1, it should do a right shift. Right shift implies it should do a, basically do a right shift. Now, there are two things that have changed from what I've explained over here. Over here, I say that you are providing an external input. But over here, I'm going to say that I'm going to provide an external input of just a 0. Now, okay, right shift. Okay, what did I explain to you in this shifting process? The output of one of the inputs is connected to the next flip-flop's input, right? We're going to do the same thing over here, but obviously a right shift. So 0, 1 implies a right shift. The output of this flip-flop should be connected to the input of this flip-flop. The output of this flip-flop should be connected to the input of this flip-flop. The output of this flip-flop should be connected to the input of this flip-flop. So you see, if these two lines are 0, 1, if you provide some input over here, I'm providing a bit 0 always. Okay? What will happen? If I provide 0, 1, line 1 is selected on each and every one of them. What are the inputs at all these lines? The input of at this mux's line 1 is the previous output of this flip-flop. The input of this mux is the output of this flip-flop. And for this mux, it is the output of this flip-flop. So provided this is 0, 1, all the outputs are going to move to the next flip-flop whenever you provide a rising edge on the clock. Clear? Questions? Say if you do not understand, I'll explain it again. I'll try to modify my statements. But did you understand what is going on over here? Why did I connect the output of this flip-flop to the input of this mux, specifically to line 1?
Because it's in parallel, or means because you want to hold it?
Yes. No. We are not holding on to the value. Hold is just this.
I thought that's true.
0, 0.
What were you pointing to?
I was pointing to this 1. Why is the output of another flip-flop connected to the input of this mux, specifically to line 1?
Because you're shifting the position.
We're shifting to the right, and in this, we are supposed to do a shift right only if the inputs S1 and S0 are 0, 1. And when these two inputs are 0, 1, line 1 is selected. Okay? Now, 1, 0 implies a left shift. Left shift implies that the output of this flip-flop should be the input now. your inputs are 1, 0. 1, 0 implies line 2 is selected. And you want to do a left shift. So the output of this flip-flop should be the input of this flip-flop specifically on the line 2 over here. So the output of this flip-flop should be the input of this flip-flop. The output of this flip-flop should be the input of this flip-flop. And I'm providing an input of a bit 0 over here. And that's why I wanted you guys to work on this, because this is a little confusing once it's completed. But if you follow step by step what we're trying to do, it's not going to be that difficult. So try to draw this right. Now what is happening over here? When it's 1, 0, the output of this flip-flop, which is over here, is connected to the second line of this flip-flop. So when it is 1, 0, this line is selected, and this line has an input of the previous output of this flip-flop. That is connected to the input of this D flip-flop, and at every rising edge of the clock, this output, which is appearing over here, will become the output over here at that clock pulse. So, what does this look like? Assuming, let's just say you do this. Follow these sequences and you'll probably see some changes. First, provide an input of 1, 1. Okay? And a parallel input of 1, 0, 1, 0. When you do this, when you provide the select lines to be 1, 1, line 3 is selected. Line 3 is selected implies I1, I2, I3, I4 are selected. They appear at these lines over here. Okay? And of course 1, 1 and a rising edge on the clock. So this is S1, S0, and this is the clock. I'm providing an input of 1, 0, 1, 0 on I1, I2, I3, and I4. So if S1, S0 are 1, 1 and there is a rising edge on the clock, the output Q1, Q2, Q3, Q4 will have 1, 0, 1, 0 because you're doing a parallel load. And this happens only at the rising edge of the clock. Okay? This will not happen if the clock is 1 or a 0 or a falling edge. It happens only if this is a rising edge of the clock, because that's how we have to design it. Now, if next I do let's say a 1, 0. 1, 0 implies it's going to do a left shift. That means all the bits are going to move to the left. Okay? So, the output right now over here, Q4, is 0. 0, 1, 0, 1. Assume that this is Q4, Q3, Q2, Q1. So Q4 is 0 right now. Q4 becomes the input of this D flip-flop because I've provided the select line to be equal to 1, 0. Okay? That means at the next rising edge of the clock, this bit is going to appear over here. This bit is going to appear over here. This bit appears over here. And an external 0 appears over here. Do you see how all the bits have moved to the left and an extra 0 has been added to the end? That's basically your left shift. Okay? Now, what if I provide another 1, 0 and a rising edge on the clock? These are the current bits at the output, and these are provided as inputs to the flip-flops. So, 0 moves over here, 0 moves over here, 1